Welcome all to the web seminar, DC Power Supply Fundamentals to Get the Most Out of Your Applications. Today, we will hear a presentation by Gary Raposa, an application engineer from Agilent Technologies. Gary has worked for Agilent Technologies and HP for over 30 years as a manufacturing engineer, R&D engineer, power test system design engineer, and now an application engineer. He also contributes to an Agilent Power Supply blog called What's Up at powersupplyblock.tm.agilent.com. In addition, we also have myself, Marlo Manalotto, an Agilent Distribution Business Development Manager, online to help answer your questions you may have during the webcast. For everyone's comfort, this is a lecture-style meeting. However, you can send questions in writing at any time during the session through the Q&A functionality of the WebEx meeting console. We'll do our best to answer your questions during the session, but may come back to you after the session if we haven't been able to. While the answer to your question may be published for others to see, we will keep your identity private. Please be reminded that this webcast will be recorded so you can review and share with your colleagues at any time. With that said, I'll now pass it over to your presenter, Gary Raposa.
Thank you, Marlo. Good afternoon to everyone, or good morning or evening, depending on where you are or when you're listening to this. So as Marlo said, my name is Gary Raposa, and I am an application engineer for Agilent Technologies. And I have been working with power supplies for more than 30 years, so I have lots of experience with these products and with the technology involved with power supplies. And I'd like to share some of that expertise with you today. We'll talk about the 10 fundamentals you need to know about your DC power supply and how to get the most out of your applications. So as you probably know, DC power supplies are used in a wide variety of applications and to test a wide variety of devices, many applications in many industries. And we like to think of the power supply is, some people have this impression that power supplies are very simple and just kind of like a battery with a knob. But as we'll see today, and as you probably know, power supplies are much more than that. We have both programmable and non-programmable supplies. Programmable meaning you can interface with a computer with the supply in order to control it. Non-programmable usually does have knobs on the front so that you can change the voltage or the current setting. Power supplies have built-in power consumption measurements, so they're able to measure the voltage on their output or the current that's flowing to the device under test, and even make power measurements in watts. Some power supplies even have the ability to create DC transients on their output, and we'll talk a little bit about that as well today. Many supplies have built-in safety protection features that are designed to protect your device under test, and they come in many different form factors. So here's the agenda for today. I'll cover three main areas or main topics about power supply usage: basic usage, connection considerations, and some advanced features. So with the basic usage, I'll talk about constant voltage and constant current operation. We'll go over remote sensing. I'll talk about using measurement built into power supplies, and also some of the protection features. And then underneath the connection considerations section, we'll look at series and parallel connections. We'll talk about minimizing noise from the power supply, how you can pay attention to the wiring, how output relays are used, and some tips about rack mounting your power supply also. And finally, in the advanced feature section, we'll go over both a measurement and a stimulus types of topics. So the measurement topic is using a built-in digitizer, and the stimulus topic will be creating time-varying waveforms using something like list mode and a power supply. So let's get right into the basic usage topics. We'll start out talking about constant voltage and constant current. Now, you need to be aware of, this is a very fundamental concept when it comes to power products, but yet it's still one that, having worked here for more than 30 years, I still run into people who get confused about this, which is why it's a good topic for me to start with today. And I always tell people that you cannot set the mode, the output mode of a supply in constant voltage or constant current. There is no button to push or setting to make to force it into one of those modes. What you do set is you do set the voltage, you program the output voltage, and you do set the current limit, so you can program the current. And the third thing that is involved in which mode the power supply operates in is the actual load that's connected across the output terminals. So those three things, the voltage setting, the current setting, and what's connected to the output actually determine which mode the power supply operates in, whether it's in CV or CC. And we'll talk about unregulated in just a moment here. But so the constant voltage mode occurs if that load that's connected to the output draws a current that is less than the current limit setting. So if the load does not require more current than the current limit setting, the power supply will be operating in constant voltage mode. And the actual current, the I out, will be determined by that V sub S. Vs is the set voltage, the voltage setting, divided by that load resistance. That's how the current will be determined. And that concept is represented in the graph here, where if you set a particular voltage and the load resistance is greater than a high load resistance, meaning if infinite, you've got zero current flowing, which is right here at the vertical axis with zero current. So if an infinite resistance or an open is applied to the output, you've got zero current, and the power supply will operate in constant voltage mode. But as you start decreasing that current, you move further and further along this line, still operating in constant voltage mode, until you finally reach this critical or crossover resistance, at which time the power supply will automatically switch from constant voltage into constant current mode, and then the voltage begins to decrease, and you're regulating in CC, or constant current mode, moving down this line at the set point, the current set point. So if you are operating in constant current mode, then the output voltage, again, is determined by that set current times the resistance that's across the output. Now, there is one other mode that does occur sometimes. It's unregulated, and that's not really a stable operating point. Neither the voltage nor the current is being regulated properly at that point, and the output can be a little bit unpredictable in an unregulated type of a mode. The possible reasons for entering unregulated mode include an internal fault with the power supply. If there's something wrong with it, that could cause unregulated, or it's possible if the AC voltage is too low, then the power supply will not be able to regulate the output voltage properly or the output current. If you're also trying to operate right on this critical or crossover resistance line, it's possible you could end up with an unregulated condition. Or sometimes there's another power supply or power source that's hooked up in parallel with the output, of which could cause an unregulated condition on the supply that you're connected to. So there are a variety of reasons that do not occur very much that would cause an unregulated condition. It's not a dangerous condition. It just would cause the output to not be regulated at either the voltage set point or the current set point. Okay, another one of the basic type of usage topics I'll cover here is using remote sense. Now, remote sense is a feature of power supplies that is used to regulate the voltage at the load instead of at the output terminals of the supply itself. So why would you want to do that? Well, as you know, lead wires have resistance. In fact, the table here shows typical resistance for some typical gauge wires. So for example, 16 gauge wire has about 4 milliohms per foot of resistance. So because there's resistance in the wires and current is flowing in them, you end up with a voltage drop across those wires, and your set voltage may not be what you, the voltage that's at your load may not be the voltage that you want, which is the set voltage that you set. And here's even a good general rule. We can see that in the table here too. For every 3 gauge increase in copper wire, you're doubling the resistance. Now I like to remember that 10 gauge wire is about 1 milliohm per foot. That way I can always kind of derive in my head, if I do need to quickly calculate what a particular wire's resistance would be for a certain length without having this chart handy. I know that 10 gauge wire is 1 milliohm per foot. It's easy to remember, 10 and the 1. And so 3 gauge increases would be 10, 11, 12, 13, which isn't shown on here, but that would be 2 milliohms per foot. And then another 3 from 13, 14, 15, 16 would double from 1 to 2 to 4. So that's, again, an easy kind of quick way to remember milliohms per foot. Now, just going back to some of the remote sense considerations, using 2-wire twisted shielded cable is always a good idea for the remote sense cables. And I will show in the next slide what that looks like. Also, you do not want to twist or bundle the sense leads together with the load leads, because the sense leads are the ones that are responsible for regulating the output voltage and controlling it, and it's possible that the load leads will have some changing current in them which could couple into the sense leads and could actually be picked up by those sense leads as noise and cause a larger amount of noise on the output voltage than would normally be there. So you want to separate the sense leads from the load leads. Also, another point about remote sensing is that most power supplies are able to compensate for a maximum load lead drop of several volts. There are some supplies that can do even more than that, but as a general rule, 1 or 2 or 3 or 4 volts is typical for the amount of load lead drop that the remote sense terminals are able to compensate for. So let's take a look on the next slide as to what that actually does look like here. So for example, 16 gauge wire, or I'm sorry, 14 gauge wire, as we saw a moment ago, has particular resistance, and 6 feet of it, which is about 2 meters, would be 15 milliohms. So if you have 15 milliohms of resistance in your load wire and an additional 15 milliohms in the return wire, that's a total of 30 milliohms. And if you have 10 amps of current flowing, then 10 amps times 30 milliohms gives us a 300 millivolt drop in our load resistors. I'm sorry, in our load leads. And if we set 5 volts, we really want 5 volts out at the load. However, that voltage drop on the wires will subtract from the voltage that's on the output terminals in this local sensing mode, and the voltage on the output will actually, or at the load, will actually be 4.7 volts, so 300 millivolts lower because of our load lead drop. And that's with local sensing, if our sense leads are hooked up directly to the output terminals. So you use remote sensing to compensate for that load lead drop. In the bottom down here, we see remote sensing where the sense leads are hooked up all the way out at the load, remotely at the load, and that way the power supply, still set for 5 volts, will regulate that 5 volts right at the load instead of at the output terminals, and it compensates for the 150 millivolts in this plus load lead and the additional 150 millivolts in the minus load lead. In order for it to do that, it automatically knows to do this. It has to raise the output voltage to 5.3 volts in order to make up for that difference. But that's exactly the way this works. It compensates for it automatically. So to implement remote sense, you would disconnect the sense terminal connections from the main outputs. That's over here in the local sensing mode. You would connect each sense terminal to the proper polarity load contact. Again, that's out here on the bottom diagram. And some power supplies do have a remote sense setting. It could be a switch or it could be an actual programmed setting. And you just need to make sure that you set it into that mode so that it does, in fact, use the remote sense terminals properly. Okay, another basic concept here is simply using the built-in measurement in a power supply for measuring either its output voltage or the output current. In this case, I'll talk about the current because that's a more difficult measurement to make. So there are several methods that people use to measure output current. One would be a standalone ammeter. Now, the advantage of that, it does have a specified accuracy. However, the disadvantage is you do have to break the circuit in order to obtain that measurement to insert the ammeter. And there's a limitation to the amount of current that the ammeter is able to handle. It could be 1 amp, it could be 3 amps, but it does not have 10 amp or 100 amp, typically does not have 10 amp or let's say 100 amp capability for a standalone ammeter. So another way in which people measure current on the output of a power supply is they might use a DMM with an external shunt. Well, the accuracy of that, it's not specified, so it depends upon the voltage measurement accuracy of the DMM, and it also depends on the shunt accuracy. There are issues with this as well. Again, you have to break the circuit in order to obtain that measurement, and there's other complications. There's thermal EMF or thermal voltages that can get created due to dissimilar metals of your connection points. The shunt has to be calibrated on a regular basis, and the shunt itself also tends to heat up with current flowing in it, and that can change its resistance. So all of that, all of those effects are unspecified and would have to be characterized in order to fully make use of that type of method to measure current. Makes it more complicated. So using built-in current measurement inside a power supply can alleviate some of these issues, if not all of these issues. So it is a fully specified accuracy, and as we can see in the table here, when you're operating near the 100% of the rated output is when you get the best type of accuracy. Could be 0.1 to 0.5%. When you're down around 10% of the rated current, the accuracy is no longer quite as good, and down at 1%, it can be near 10%. So normally you want to operate a power supply or make use of the current measurement when you're up in the 50 to 100% of the rated output current, and that way you'll get the best performance from your current measurements. And the nice thing about using the built-in measurement in a power supply is for measuring current is there's no need to break the circuit and there's no additional connections that are needed in order to make your current measurement. Okay, the last of 4 basic usage topics I'll cover here today has to do with the built-in power supply protection features, which enable you to safeguard your device under test. Many times your device under test is sensitive, and it could be sensitive to potentially damaging voltage or potentially damaging current, a high voltage or a high current. So there are 2 main protection features in many modern power supplies, over voltage protection and over current protection. And as the terms imply, the over voltage protection protects against excessive voltage. Now, so the idea there, of course, is if the output voltage of the supply exceeds the OVP setting, then the OVP will trip and it will turn off the output of the supply, protecting the device from an excessive voltage. Now, one thing to note that's important is typically, not always, but typically the OVP responds to the voltage at the output terminals of the power supply and not at the sense terminals. So if your power supply does have an over voltage protection circuit that does respond to voltages at the output terminals, you may want to set the OVP setting high enough to also account for any load lead voltage drops that you might have. So as we saw a moment ago, you could have 300 millivolts higher voltage on the output terminals than on the sense terminals if you've got 10 amps flowing in 6 feet of, let's say, 14-gauge wire. Now, the OVP also responds quickly in microseconds. It's able to detect that voltage and begin action in microseconds. The thing that it really cannot do in that time frame necessarily is bring the voltage down that quickly, but at least it's able to detect the voltage, the excessive voltage, and begin the response to it. Again, depending on the supply, some may take a while, meaning could be milliseconds or tens of milliseconds for the voltage to begin to come down. It also depends on how much load, how much current is being drawn from the supply as to how quickly the voltage will decrease. Another important protection feature is OCP, over current protection, and that is different from simply constant current mode. In constant current mode, the supply will hit that current limit and it will prevent more current than the current limit setting from flowing to the device, but it will not turn the output off. Once you turn overcurrent protection on, when the supply hits CC mode, it'll actually trip the OCP, the overcurrent protection, and it'll turn off the output. And that will protect your device from having excessive current flowing for an extended period of time, which could, in fact, burn something up potentially. Okay, let's move on to some connection considerations. First one has to do with increasing the power from a power supply, and there's 2 ways to do that. One is to increase the amount of voltage that's available, and the other would be to increase the amount of current. So to get more voltage, you would use a series connection to get more voltage. And that's just a matter of hooking the plus output of one supply to the minus output of another supply, and then running the plus output of this top supply in the diagram over to the load, and then the minus output of the bottom one over to the load. And that essentially doubles the amount of voltage that you have available from a single supply. The way in which you would program these is you would set each power supply output independently so that the voltages sum to the total desired value. and typically you set them to the half of, if you have two supplies in series, you would set each of them to half of your desired voltage. If you have three, you would set them to 1/3. Typically you want the voltage on each of the series supplies to be the same. There are some cautions about this. You do not want to exceed, there's a floating voltage rating of many power supplies. Most Agilent supplies have a float voltage rating of 240 volts DC. So that's the maximum rating of the output terminals to ground, to chassis ground or to earth ground. And you just want to make sure that you, when you start increasing the total voltage by connecting things in series, that you do not, in fact, exceed that output terminal isolation voltage. The other thing to pay attention to is you don't want to apply a reverse voltage to the outputs of the power supplies, or if that does happen inadvertently, you want to make sure that there's some protection built into the supply, like a reverse protection diode. So for example, if this load shorted by accident, let's say you're testing something and it didn't work correctly, and the load that you have out here, your device under test, actually shorted. If you look carefully at this, the output, the plus output of this top supply, if this is a short here, the load is connected to the minus output of the bottom supply, and vice versa for the top supply negative output and the bottom supply plus output. So these are, if the load is shorted, these are actually hooked up backwards to each other, plus to minus and minus to plus. And so you could force a reverse voltage across one of these power supplies if in fact this load did short. So all Agilent power supplies do have a reverse protection diode in order to protect the output from voltage in a negative direction, which could potentially damage some of the output components inside the supply. Another consideration is you want to connect outputs in series that have identical voltage and current ratings. And the reason for that is if you do end up with a situation where, let's say, the load shorts, the full current from one supply could flow into that reverse protection diode in the other supply. So the reverse protection diodes are actually designed to handle the full current from one of the supplies. And so if you had unequal supplies, let's say one was capable of 10 amps and the other was capable of 100 amps, it's possible that the 100 amp supply could force excessive current through the reverse protection diode and could actually damage it. So that's why we always recommend that you connect outputs in series that have identical voltage and current ratings. And this diagram does show, using remote sense, you would hook up the remote sense cables in such a way that they accommodate the series connections as well. And it's very simple, shown in the diagram here. So that series power supplies was to get more voltage. If you need more current, you would hook power supplies up in parallel. And the connection configuration is shown in the diagram here, plus to plus and minus to minus, hooking them up in parallel. Same thing with the remote sense. The remote sense leads get hooked up in parallel, and then from one of the power supplies it gets run out over to the load. Here you would want to set the current limit of all of the outputs equally so that they sum to the desired current limit value. So since each of the supplies will be contributing to the current, and let's say you wanted a 10 amp current limit, you would set each of these to 5 amps so that they sum up to the total 10 amps. You also want to have only one of these supplies can be operating in constant voltage mode to control the voltage. Otherwise, they would be fighting with each other for control, and that's not a good situation to have. So what you want to do is you actually want to set one of the voltages slightly lower, it's actually lower, than the outputs that will be operating in constant current mode. And that way it can sink, some power supplies have the ability to sink current, so if you set the voltage a little bit lower, they can pull current. That particular supply, if it's this top one, can pull some current from this bottom supply, and the top one would actually regulate the voltage. The bottom one would be operating in constant current mode. So the load also, in certain parallel situations, you want to make sure that the load is drawing a minimal amount of current to keep the CC supplies in CC mode. Once again, we recommend that you connect outputs of identical voltage and current ratings. A similar reason that was true for the series supplies. You could potentially damage one or the other depending on any fault conditions that might occur. Okay, another connection consideration is how to use wires both for remote sense and for the load leads. So in order to minimize noise. Now the best way to minimize noise is to start with a low noise power supply, because removing the noise or preventing the noise afterwards is more difficult than simply starting with a supply that does have low noise to begin with. So both RMS noise and peak-to-peak noise specifications should be considered when choosing a low noise supply. Now, having worked here for more than 30 years, I have seen a transition from linearly regulated supplies to switch mode power supplies. And there are many people who still have the impression that switch mode power supplies are noisier than linears. And in general, it's true, but we, at Agilent anyway, we have done a tremendous amount of work to make our switching power supplies have output noise specifications that are very similar to linearly regulated supplies. So you would have a difficult time distinguishing one of our switching supplies from a noise performance perspective from some of the linear supplies that are out there also. Because the modern switch mode power supplies do have performance that is very close to linears. But what you can do on the output to prevent noise pickup is use shielded two-wire cables. Now, both for the sense leads and even for the output leads as well. It's probably more critical on the sense leads than the output leads, but both will help. Now, I mentioned it earlier also, you don't want to bundle these together. The sense leads and the output leads should be twisted with each other, the sense plus sense and minus sense, and the plus out and minus out. However, you don't want to bundle the load leads and the sense leads together, because there could be coupling between the two that would cause some interference and extra noise. Now, the other important thing to look at here is the shields are connected only at one end. So you'll see there's a ground connection to the shield here, and on the other end, the shield is left open. That's because if we look at the diagram on the right-hand side here, if you hook up the shield to ground on the left side right here, and also on the right side out at the DUT, it's quite possible that these earth ground locations will have a slight difference in voltage, and that delta V will create current to flow, a ground loop current in the shield itself, and that can also get picked up as noise and show up on the output of the power supply. So you actually do not want to do what's shown on the right-hand diagram here. Don't want to do that. One last consideration about minimizing noise, and this has to do with common mode current, is you would like to balance the output to ground impedance both from the plus terminal and the minus terminal. That way, if there is common mode current that flows out of the supply and into the load leads, it shows up as a equal drop on those load leads and doesn't show up as a differential output voltage, which will show up as noise on the output. So if you can keep the impedance the same or very similar from the plus terminal and the minus terminals, that will help to minimize noise also. Okay, another consideration with respect to connections is related to output relays. Now, I've run into some applications where people believe that if they shut the output off, not the power switch, but if they say to their power supply, output off as a command, that there's nothing, and their device under test is still connected, they might think that there's no connection anymore to their device under test, or there's nothing that will interfere with their test saying output off. However, if you really want to completely eliminate any interaction between your device under test and the output of the power supply, you really want to put relays to have a complete galvanic disconnect between the device under test and the output of the power supply. So make sure that your test is not adversely affected by believing that the output off creates that situation where it's a complete galvanic disconnect. There are devices that are sensitive to the extra capacitive loading that the power supply output could put on that device under test, and with output off, that extra capacitance is not removed. Some devices have a changing voltage on them, and that output capacitance in the power supply might actually draw current from that device under test. You know, when the supply is off and a different test is being done on the device under test, it could have some voltages on it that are changing. So there are even some different locations of relays, and you should be aware of this depending upon the power supply and the vendor that produces them. It's possible that the output relays are right here on the output terminals, and in this case, when they're open, the device under test is no longer connected to any of these internal components. However, sometimes, and Agilent does make power supplies that are like this, the relays are inside or inboard of some of these other components that are on the output, even the output capacitor or these other RFI, which is radio frequency interference networks, and ESD, electrostatic discharge filters, that have to be as close to the output as possible excuse me, to prevent RFI from getting out of the supply and interfering with the radio signals that people do want to listen to. So these RFI and ESD components need to be really, really close to the actual output terminals, and that's why sometimes these relays are placed inboard of that in order to prevent the RFI. We still want we still have to meet RFI specifications and ESD specifications as well. So just be aware of that. Okay, the last kind of connection consideration topic I'll go over here has to do with rack mounting your supply. So typically power supplies are one of the heaviest components in a test system, and because of that, we frequently put them at the bottom of the test system in order to properly distribute the weight in that test system. Unfortunately, I have even seen people who had a bad weight distribution in a test system once, and as they were moving it in a hallway, it caught on a barrier between two different sections of the hallway, and unfortunately it tipped over. That was not a good situation. So you do want to make sure that the weight is distributed properly to avoid rack instability. Another tip about rack mounting is considering the AC input power. So you do have to provide adequate AC input to avoid excessive current draw. Heat management is a big deal also. Power supplies, obviously, they produce power. They also consume power. Many modern supplies are very efficient these days. However, they still do dissipate heat internally, and so that heat has to be managed. Now, so you want to pay attention to the airflow. Many supplies have cooling fans, and they'll draw air in from the side, typically air in from the sides and out the back. So you do want to pay attention to how you want to manage that heat flow. Magnetic interference is another consideration. Not so much these days for things like in the old days there were CRTs, cathode ray tube type devices. So there were oscilloscopes that had CRT screens. There were monitors that were CRT monitors. And power supplies can have large magnetic fields that come out of them. And I have seen that those magnetic fields interfere with a scope screen or with a monitor for a computer that's built into a rack also. So you just want to make sure that you don't mount your supplies close to something that might be susceptible to a magnetic field coming out of that. Of course, these days there's more LCD displays which don't have that tick-up problem. They're not anywhere nearly as sensitive as a CRT screen. Now, even voltmeters, so a sensitive voltmeter, even though it's designed to be immersed in a certain magnetic field, if the magnetic field is high enough, the circuitry inside a voltmeter, for example, could be influenced by a large magnetic field. So you just want to pay attention to where you mount a high power supply that might produce a large magnetic field inside. And of course, routing wires is always a consideration. I mentioned a couple of times already, you do want to keep the load leads separate from the sense leads on a power supply in order to minimize both conducted and radiated noise. So two last topics, advanced features. One has to do with measurement, and this is using not all power supplies do have this feature, but more advanced ones do, where they're able to digitize both their output voltage and their output current, and that way you can capture waveforms using the built-in digitization. And typically there's 3 parameters that can be set with a digitization feature that's in a supply. And these are interdependent, so once you set 2 of these parameters, the third is determined. So you can set the time interval between measurement points. You could set the number of samples or the number of points you want to take, and or you could set the total acquisition time. So of course the time interval that you set times the number of samples minus 1 will give you the total acquisition time. So that's the relationship between these 3 parameters. But so you can set 2 of these, and the third will be determined. Now, these are useful for things like capturing waveforms, and here's a good example of measuring the cell phone current drain using a power supply instead of the battery. So in this case, battery was removed from the cell phone, and we used one of our power supplies in order to characterize the current that is drawn from the cell phone under different operating modes. So for example, we see here that the idle current could be measured, the receive current is measured, and the transmit current pulses are seen here as well. So some power supplies even have a display on the front that enables you to see a scope-like view, just like we see here in the slide. Others may have the ability to digitize the voltage and/or current, but you would need to bring that data back to a PC and then plot it using some software in order to actually visualize the current or voltage waveforms. And you can do things like pre-triggering and post-triggering in order to acquire the exact data that you're looking for. So the last topic with respect to advanced features that I want to talk about is using something called list mode in a power supply, and that can be used for creating arbitrary waveforms on the output. So to create a list, you would set one or more voltage or current steps in order to define what those output will look like over time. You'd also set dwell times for each one of those list steps, and you can even set something like the repeat count, which would determine how many times it would repeat that particular waveform. So for example, you could create something that looks like what's shown in the top diagram here, where this shows a repeat count of 2, and it shows a 5 or 6, let's see, 1, 2, 3, 4, 5, 6 step waveform. Now, another example of when this is useful is creating waveforms that you want to subject something like an engine control unit, let's say, when doing automotive testing. So this is an example of a cold crank voltage profile. So cold crank means when you start up the car, the battery voltage drops substantially down to this low value as the car as the starter motor is turning over the engine, and then it recovers and plateaus for a while, and finally as the engine kicks in, it settles back out to a final value here. So in the automotive industry, many of the electronic components that are inside a car have to be tested to make sure that they do not misbehave when subjected to this cold crank voltage profile. And there are power supplies that can create this type of a waveform, and that's very useful in doing that type of testing. So all of the topics that I have covered today are actually talked about in this application note, which is called 10 Fundamentals You Need to Know About Your DC Power Supply, and the link is shown on the slide here. So if you do want more details about any of these topics or all of them, I would encourage you to download that application note and take a look at it. It does have much more information in it for each of these topics than what I covered today. For even more information, there are a variety of application notes that we have. We have an app note on decreasing test time for power supplies. There's another one that does show an additional 10 practical tips. We've got one on understanding linear power supply operation. There is also a much longer piece of literature called this Test System Development Guide. That's, I think, about 200 pages, and that covers more than just power products, but it has a lot of really useful information about developing test systems. And as Marlo mentioned earlier, I do contribute roughly each week. I write a blog for, excuse me, our What's Up blog, and that's dedicated exclusively to power supply types of topics. And we also have literally hundreds of videos on YouTube. We call it Agilent Tube, and the link to take a look at those is here as well. And those also cover topics that are beyond just power. Certainly there are power supply topics on there, but we go into all of the other test and measurement type of topics that would be relevant. So finally, I just want to say that I hope you do appreciate the fact that a power supply certainly is more than just a battery with a knob. All of the topics that I covered today apply to the more than 200 power supplies that Agilent does make, and we have more than 60 basic supplies and more than 160 high-performance supplies. So most likely we have something that would help in your application. And with that, I'd like to open it up to any questions you guys might have, and I'd also like to just even thank you for attending today. So let's see if we've got some questions.
All right. Well, thank you very much, Gary. And as Gary mentioned, it is time for questions and answers. So you can send questions in writing now through the Q&A functionality of the WebEx meeting console. We'll do our best to answer your questions during the session, but may come back to you after the session if we have not been able to. While the answer to your question may be published for others to see, we will keep your identity private. So we do have a few questions, Gary. The first one is, how do power supply measurement accuracies compare with standalone DMMs, and what are the trade-offs?
Oh, okay. How do power supply measurements compare? Well, the standard DMM will likely have better accuracy than one of our power supply measurement the accuracies built into the power supply. So we can do both voltage and current measurements with our supplies, and quite honestly, probably 90% of the time, the accuracy of our voltage and current measurements is good enough for a particular application. But if somebody needs really, really, really high accuracy, like 0.001% rather than 0.01%, they may want to use an external voltmeter or something to measure current. It's more complicated because you have to use a voltmeter in combination with something like a shunt. And as I mentioned earlier, there are some issues with shunts. They can drift. You have to make sure that you fully characterize that. So the other trade-off you might have to make is switching time. So for example, built-in measurements will be typically faster because you do not have to switch the voltmeter over to whichever output you want to measure, or you do not have to switch the current shunt to the voltmeter using external switching. So built-in measurements are simpler, there's less wiring, they are less costly. However, if you need really, really, really high accuracy, you probably do want to go to an external measurement system.
Okay, great. The second question we have is, what bandwidth can power supplies support for arbitrary waveform creation?
Ooh. Okay, well, first of all, not all power supplies do have arbitrary waveform creation. So I suppose with one that does not have that ability, the answer to how much bandwidth would there be would be zero bandwidth. It just puts out DC. So, but for the highly capable supplies and the high-performance power supplies that do have arbitrary waveform capability, the answer as to what is the highest bandwidth or what is the bandwidth, it depends on the supply itself. So again, Agilent has the really high-performance supplies can go up to 50 to even 100 kilohertz of bandwidth on the arbitrary waveform generation. You know, you're not going to get bandwidths that are comparable to a function generator of a few megahertz, because moving power, that amount of power around at a few megahertz is very difficult. But like I said, the highest bandwidth that we can produce is roughly 100 kilohertz. It depends on which supply you're using. Some of them are actually hundreds of hertz to thousands of hertz to tens of thousands of hertz, and the maximum being roughly 100 kilohertz.
Okay, great. Thank you. All right, I don't see any more questions from the Q&A functionality, but if you do have any questions after the event or want to ask more questions offline, please don't hesitate to contact us at the address provided. In a few seconds' time, when I close the event session, an evaluation form will pop up on your screen. We do appreciate your feedback. So with that said, thank you again for your attendance, everyone, and I wish you a nice continuation of your day. Goodbye.